Beneath the sands of Dubai, before a single steel beam was lifted, before the world's tallest tower even had a name, engineers faced a problem that had nothing to do with height. It had everything to do with what was underneath. The site chosen for the Burj Khalifa was not solid bedrock. It was not stable ground carved from ancient stone. It was a mix of weak limestone, loose sand, and highly compressive layers sitting above a water table filled with salt. In simpler terms, the ground beneath what would become the tallest structure ever built by human hands was, by engineering standards, deeply problematic. To understand why this matters, think about what a super-tall skyscraper actually does to the earth below it. It doesn't just sit there, it pushes. It concentrates an almost incomprehensible amount of weight onto a single footprint. The Burj Khalifa was designed to rise more than half a mile into the sky. It would eventually carry over 500,000 tons of dead load. Floors, glass, steel, concrete, everything inside and around it, pressing straight down into whatever the ground could offer. And what the ground in this part of Dubai could offer was not much. This is the part of the story that never makes the highlight reel. No one films the soil. No one builds a documentary around compressibility tests and groundwater readings. But without solving what was down there first, nothing above it would have survived. The Burj Khalifa's foundation is not a footnote to the tower's story. It is the story. The challenges stacked up fast. Soft layers near the surface meant that uneven settlement was a real risk. Different parts of the building sinking at different rates. This would crack the structure from the inside out over time. The aggressive saltwater sitting in the soil was corrosive enough to eat through conventional concrete and steel reinforcement. The desert heat, pushing past 120 degrees Fahrenheit in summer, created additional stress on any material exposed to the environment. And then there was the sheer scale of what needed to be supported. A building so heavy and so tall that the engineering calculations required for its base had never been performed before at this level. The team at Samsung C&T, Arab Tech, and Turner Construction, working with structural engineers at Skidmore, Owings, and Merrill, knew they were not solving a standard foundation problem. They were writing a new chapter in what foundation engineering could actually accomplish. Before a single pile was driven, before a single cubic yard of concrete was poured, they had to go down, deep down, and understand exactly what they were dealing with. Before any construction equipment arrived on site, before the cranes and the concrete trucks and the steel crews, a quieter and far less glamorous operation was already underway. Geotechnical engineers moved across the future footprint of the Burj Khalifa with drilling rigs, soil samplers, and groundwater testing equipment. Their job was not to build anything. Their job was to understand. This phase is called a geotechnical investigation, and on a project of this scale, it was one of the most critical decisions the entire team would make. Get it wrong, and every engineering solution that followed would be built on false assumptions. Get it right, and you had a fighting chance of putting 500,000 tons of tower on ground that had no business holding it. The team drilled deep bore holes across the site, pulling up core samples from multiple layers of soil and rock. What they found confirmed their concerns. Near the surface, the ground was weak and inconsistent. Loose sand and compressible fill sat above layers of calciciltite and weak sandstone, a type of soft limestone formation common across this part of the Arabian Peninsula. These materials had low bearing capacity, meaning they could not simply absorb heavy loads without deforming. Deeper down, the rock became more competent, more dense, more reliable. But reaching it would require going down approximately 50 meters, nearly 165 feet below the surface. The groundwater situation made everything harder. The water table in this area of Dubai sits close to the surface, and that water carries a high concentration of chlorides and sulfates. Essentially, a slow-moving chemical attack on any concrete or steel left exposed to it. Standard construction materials would deteriorate far faster than the building's intended lifespan. The engineers were not just dealing with weak ground, they were dealing with hostile ground. Every core sample was analyzed in the lab, compression tests, permeability tests, chemical composition tests. The data was fed into computer models that simulated how the soil would behave under the tower's projected load. Engineers ran scenario after scenario. What happens if this layer compresses more than expected? What happens if the water table rises? What happens over 50 years of sustained pressure? The models had to account for not just the weight of the building, but the way that weight would shift during wind events, when the tower sways, when thermal expansion causes the structure to move. What came out of this investigation was not just a report. It was a blueprint for survival. The soil could not be changed, but now, at least, it was understood. And with that understanding, the engineers finally knew what they had to build. The answer to everything the geotechnical investigation revealed came in the form of steel and concrete driven deep into the earth. Not a slab, not a mat, not a surface foundation of any kind. Piles, hundreds of them, bored straight down through the weak upper layers and into the competent rock below, where the ground could finally be trusted to hold. The Burj Khalifa's foundation system uses 194 bored, cast-in-place piles. Each one is 1.5 meters in diameter, roughly 5 feet across, and reaches approximately 50 meters below the surface. To put that in perspective, you could stack a 15-story building inside the depth of a single pile and still have room. These are not decorative anchors. They are the primary load-bearing system for the most ambitious vertical structure ever constructed, and every one of them had to perform without failure for the lifetime of the building. The process of installing them was slow, precise, and punishing. A rotary drilling rig bored each hole through the layered ground, cutting through sand, weak limestone, and increasingly dense rock until it reached the target formation. Because the groundwater was aggressive and the surrounding soil unstable, the holes had to be kept open during drilling using a dense fluid called bentonite slurry. This slurry filled the borehole and counteracted the pressure of the surrounding ground and water, preventing the walls from collapsing before the concrete went in. Once the hole reached the required depth, a steel reinforcement cage was lowered inside. Thousands of pounds of rebar assembled into a cylindrical skeleton that would give the concrete its tensile strength. Then came the concrete. Not standard concrete. A specially designed high-performance mix with a low water-to-cement ratio added silica fume and chemical admixtures that made it resistant to the sulfates and chlorides in the groundwater. This mix was poured from the bottom up using a tremie pipe, displacing the bentonite slurry as it rose and filling the entire borehole without trapping air pockets or contamination. The result, once cured, was a column of reinforced concrete, harder and more chemically resistant than anything a standard mix could produce. The 194 piles were arranged in a pattern that followed the tower's distinctive Y-shaped footprint, concentrating support directly beneath the areas of highest load. Together, they created an underground forest of concrete columns, invisible to anyone standing above, silently transferring the weight of the sky to the only ground strong enough to accept it. 200 piles driven into the earth solve one problem. They create another. You now have 194 separate columns of concrete, each carrying load independently, each sitting in slightly different soil conditions, each capable of settling at a slightly different rate. Connect a 500,000-ton skyscraper directly to that arrangement, and you risk exactly the kind of differential settlement that the geotechnical team spent months trying to prevent. The building could tilt, it could crack. Over decades, the damage would compound. The solution was to tie everything together into a single unified base. Engineers designed a massive reinforced concrete raft, a continuous slab poured across the entire footprint of the tower, connecting the tops of all 194 piles into one rigid platform. This raft is 3.7 meters thick, nearly 12 feet of solid reinforced concrete, covering approximately 8,000 square meters of ground. It is one of the largest single concrete pours in construction history. The logic is elegant. When one pile experiences slightly more settlement than its neighbors, the raft redistributes that movement across the entire system. No single point bears a disproportionate share of stress. The building above behaves as though it is sitting on a perfectly uniform foundation, because for engineering purposes it is. The raft is not just a connector. It is a load balancing machine. Pouring it was one of the most carefully managed operations of the entire project. The volume of concrete required was enormous. Over 12,500 cubic yards delivered and placed in a continuous pour that ran for nearly 4 days straight without stopping. Stopping would have been catastrophic. Concrete cures through a chemical reaction that generates heat, and if a pour is interrupted, the joint between old and new concrete becomes a structural weak point. On a foundation expected to last a century, weak points are not acceptable. The heat was the other enemy. Dubai in summer is brutal, and concrete in extreme temperatures cures too fast, which causes cracking. The team chilled the mixing water, used ice in the concrete mix, and poured during nighttime hours whenever possible. Temperature sensors were embedded throughout the slab to monitor the curing process in real time. Engineers watched the heat signatures around the clock, ready to intervene if any section began to overheat. When the raft finally cured, it sat there beneath the desert, invisible, unglamorous, and absolute. Every column, every floor, every pane of glass that would eventually rise half a mile above it rested on this single continuous platform. The tower had its foundation. Now it could begin to climb. The foundation was in the ground. The raft was cured. But the engineers knew something that the construction timeline could not fix, and no amount of careful pouring could change. The ground around and beneath the Burj Khalifa was going to keep fighting back. Not dramatically, not all at once, but slowly, chemically, and without pause, for the entire life of the building. The enemy was the water. Specifically, the groundwater sitting just below the surface of this part of Dubai, carrying concentrations of chlorides and sulfates aggressive enough to qualify as some of the most corrosive soil conditions found anywhere on Earth. In standard construction, reinforced concrete is considered durable. Steel rebar embedded inside a concrete column is protected by the alkaline chemistry of the concrete itself, which forms a passive layer around the steel and prevents rust. But introduce enough chlorides into that environment, and the passive layer breaks down. The steel begins to corrode. Corroding steel expands, cracking the concrete from the inside, and once concrete cracks, more water enters, accelerating the process. Left unchecked, this cycle can compromise a structure in decades rather than centuries. The team approached this on multiple fronts simultaneously. The concrete mix itself was the first line of defense. The same high-performance formula used in the piles, low water-to-cement ratio, silica fume, chemical admixtures, created a matrix so dense that water and dissolved salts could barely penetrate it. Permeability tests confirmed that this concrete was many times more resistant to chemical attack than standard mixes. But the engineers did not stop there. A cathodic protection system was installed throughout the foundation. This technology works by running a small electrical current through the concrete, counteracting the electrochemical process that causes steel to corrode. It is the same principle used to protect ship hulls, pipelines, and offshore platforms, industries where aggressive water contact is a permanent condition. Sensors embedded in the foundation monitor the system continuously, and the current can be adjusted as conditions change over time. Waterproof membranes were applied across exposed surfaces of the raft and the pile caps, adding a physical barrier between the concrete and the surrounding soil. Drainage systems were engineered around the foundation perimeter to manage groundwater levels and reduce hydrostatic pressure against the structure. None of this is visible. None of it photographs well. But without it, the most spectacular tower ever built would have begun quietly destroying itself from below on the very first day. The foundation was not just built to carry weight, it was built to survive. When the Burj Khalifa opened in January 2010, the world looked up. News cameras pointed at the sky, crowds gathered on the ground. Every photograph taken that day showed the same thing. A tower rising so far above Dubai that it disappeared into the haze before it ended. Nobody photographed the ground. nobody celebrated what was underneath. And that is exactly how good foundation engineering is supposed to work. The foundation's job is to be forgotten. It succeeds when nothing goes wrong, when the building above it behaves exactly as the models predicted, when settlement is uniform and controlled and measurable in millimeters rather than inches. By every available measure, the foundation of the Burj Khalifa has done its job. The tower has settled, as all tall buildings do, but within the margins the engineers designed for. The structure above remains plumb. The glass curtain wall has not cracked from differential movement. The mechanical systems in the basement levels have not been compromised by groundwater intrusion. The building works because the ground holds. But the full weight of what that foundation carries is worth stopping to consider. The Burj Khalifa transfers over 500,000 tons of load into the earth below. On a windy day, the tower sways, intentionally, by design, and that movement shifts the load distribution across the pile system in real time. Temperature changes cause the steel superstructure to expand and contract, sending different stresses down through the concrete core and into the raft below. The foundation absorbs all of it, constantly, silently, without a single visible sign of effort. The engineering decisions made in those early geotechnical reports, the pile depths chosen, the raft thickness specified, the concrete mix designed, the cathodic protection installed, those decisions will continue to matter long after everyone involved in making them is gone. Design life of the Burj Khalifa's foundation is measured in centuries. What was solved in the soil of Dubai in the mid-2000s was not just a construction problem. It was a bet placed on behalf of the future. This is what separates iconic structures from merely tall ones. The Eiffel Tower is remembered for its iron lattice, the Golden Gate for its cables. The Burj Khalifa will always be remembered for its height. But the reason any of it stands is never the part you can see. It is always what was done first. Underground, out of sight, before the first beam was lifted toward the sky. The foundation is not where the story ends. It is where it begins.